Hello and welcome to our Feedback Control System's final projects. We're going to be talking to you about cranes. And this is our team.
I'm Will.
I'm Chris.
I'm Michael.
I'm Andrew. Our model for this project is a crane with three basic components: a tower, a jib, and a suspended load. The tower rotates the load around its pivot, and we have to reduce the error and overshoot in the system.
Oh, hey, I didn't see you there. Today we're going to be talking a lot about cranes, so we brought a bit of a model to help you see exactly what we're going to be modeling and taking care of in terms of this feedback project. So today we're looking at the input being the motor at the base as it turns and torques the crane around in a radial direction. So what we're modeling is the tower of the crane, how it's going to twist when you move and apply force to it, the jib of the crane, as that's going to react to the change in direction, both from the motor and from a wind input. And then finally, the load, which in this case is a hook, but is going to be something like a wrecking ball in terms of our model. So we're modeling how this is bending, and then also the cable that runs down to the load right here is going to be swinging back and forth. So we're taking all those things together, putting it in a model, and you'll see the results as we go on in this presentation.
So as Will talked about in our video segment there, we have a couple of concerns here. First off, the input of our system is going to be the angular position of the motor, and the output of our system, as you can see, is the angular position of the wrecking ball or the load of whatever it is.
On this diagram, the first spring damper system represents the beam as well as that inertial component. The second spring damper system represents the wire, and the third is the wrecking ball.
And Chris, what did we use to come up with those constants down there?
Great question, Andrew.
Thank you.
For the constants for the beam, we used an equation for the spring constant of a solid beam, and then we got the damping coefficients from that. The inertial component was just calculated from the mass of the beam and material properties. The second spring damper system was a little bit harder because first we modeled it as a solid cylinder, but then we decided that we should choose constants just based on how the plot looked to make it model more like a wire.
And all those values were calculated based off of actual crane values, right?
Correct. We used a real life crane to model these values.
Yeah, and actually it's interesting. The cable is a little difficult to model because when you're looking at just the radial position of it, you can't really talk much about the properties of the wire stretching as much, but it's more just kind of modeling the back and forth movement, which is kind of why, as we talked about, we sort of just, looked to see at the response. We actually found how long it would take a pendulum of the same length to make one full, revolution omega-wise, and then model our system to fit with that behavior, the real-life behavior of a big swinging load. So that's why those kind of seem hand-wavy, but there's a reason for those as well.
And we'll see a plot of that later, right?
Yes, we will.
So this is the impedance network of our model. This just is a transfer function as well with all the constants listed earlier.
After listing this as an impedance network, we can thankfully go ahead and take these constants, plug them into MATLAB, and generate plots and stuff for our open loop system.
So here we can see the model we just came up with, but instead of all the constants, we put in the numerical values that we calculated a couple of slides ago. And again, you can see the input, the angular position of the motor, to the output, which is the position of the crane wrecking ball.
So in terms of analysis on our crane, there were a couple of things that we had to consider. First off, what does the input actually look like? We also wanted to go ahead and consider if there were any disturbances that this crane might feel, and a couple of other considerations as well. We chose to model our motor position input as a step function because the motor is going to be alternating from off to on, so it'll just immediately turn on and then provide an input to our system. Additionally, we chose to decide that our crane, being up in the air very high, will probably be feeling some wind disturbance. We chose to model that wind disturbance as a step function as well, because in reality, wind's going to be varying a bunch, but we wanted to go ahead and proof our crane against the worst case scenario, which is a constant high-speed wind that it'll have to resist.
Using MATLAB, we created this root locus plot, which determined for us that this plant by itself was bivostable because it had no right-hand plain poles and just left half plane poles.
However, this does not mean that our design goals are met. As you can see, we still have a very high percent overshoot and a large settling time. Obviously, this is not ideal for a crane, so we aim to reduce the percent overshoot to 3%. We want to reject disturbance from the wind, as mentioned previously, and we want to get the settling time down to under 10 seconds.
So all three of these points are super important because the overshoot, you don't want your load swinging around dangerously. And the wind is obviously a very real consideration in the physical world. And the settling time is important because if it's a crane, you're dealing with a construction site where time is money.
Boy, I love cranes. But what I like more than that is cranes that work. Because cranes that are out of control are a bad time. What we're working about in this project has to do with, as we said before, the percent overshoot, the settling time, and rejection of wind disturbances. So I'm here to give you a little physical feedback of what exactly each of those means. So for settling time, let's say our arm turns. You can see the weight moving around and taking time to settle into its final position. We want to reduce that as much as possible so we don't have a big wrecking ball swinging around the whole time. Second, wind rejection. Let's say a hurricane moves in, or just a slight gust. Up at 400 feet or wherever your crane is going to be, it's going to have a lot of effect. So let's say it pushes your crane a little bit to the side. You want to have the system so that it doesn't care whether or not that happens. In other words, the disturbance rejection. And finally, probably one of the most important points is percent overshoot. We want to make sure it's low because in a real crane system, if you swing your arm from here to here, you don't want it smashing into the building off to the side because as we can see, you smash and bad things happen. This factors in a lot into social justice considerations because on a construction site, you have a lot of other people to worry about. The orphanage down the road, an apartment building right next to your construction site, you don't want to knock down either of those because you'll be hurting people's lives and costing people a lot of money. In other words, we want to make sure this system is safe, stable, and easy to use.
These are our design goals illustrated. This is adding in the settling time and the percent overshoot. As you can see, we can move our poles around and change the phase margin to get our poles within this region. Therefore, we know we can design a system that will meet our requirements.
Now we go ahead and go to the design and verification part of this project. Specifically, what we ended up doing was closing the loop of our crane, and we had to go ahead and choose a controller that would meet all of our requirements. Initially, we decided to go ahead and choose a PI controller because we thought that this would decrease the rise time and sort of meet our requirements. What we did not anticipate, though, was that by choosing just a PI controller, the overshoot was a little bit too high still. To that regard, we ended up adding in a D, so we ended up doing a proportional integral derivative controller as well. Adding in the derivative term went ahead and decreased our overshoot to meet our requirements, and as you can see here, we ended up choosing a couple of specific values for those gains. These are all sort of driven by initial mathematical calculations. Then we went ahead and iterated through in MATLAB to come up with values that would actually meet our specific requirements.
We can see here kind of the proportion between the different gains that we have. We had a lot of trouble with our percent overshoot, so our derivative controller is really high. And that also helps with the settling time, which is another one of our key concerns.
And using MATLAB, we were able to plot the final results of our control system with the disturbance tracking to a new angular position. As you can see, our final percent overshoot was under 2%, and our settling time was under 10 seconds, both of which are within our design goals.
Additionally, in terms of disturbance rejection, you can't really see it pictured here, but we've included the other graph without the disturbance in our written component of the report. The two graphs are very, very similar, which means that our crane does a very good job of rejecting any disturbance that the wind might add. Last but not least, as you can see, here are our references. A lot of these are responsible for getting the physical constants that we talked about earlier, the spring constant, the damping coefficient, etc. They have the equations that we got those from.
Oh my god, it's a crane. Thanks for watching our video.
Yeah, we enjoyed having you here and hope you like cranes as much as we do.
Have a great break.
Bye.